Welcome to the introduction of the structural selection principle. This isn't mere sci-fi. It is grounded in real science. A thought-provoking question in modern physics arises. Why are certain natural structures stable and endure over time? Other mathematically valid but unseen possibilities exist. Dynamics help us understand the world by observing motion. We calculate and analyze a system's evolution over time. But an interesting problem emerges here in this situation. Theories possess many mathematically allowed solutions. Equations provide a variety of configurations and solutions. Yet, only a small subset of these ideas are actually realized. Why are some solutions still effective and relevant today? This is precisely where the principle truly begins its journey. The fundamental concept behind this idea is surprisingly simple. Structures vary greatly in overall quality and durability. It is possible that one specific state may be more robust. This describes a theoretical layer that exists above dynamics. Mathematically, we introduce a new cost function for analysis. Small values suggest that there is high structural coherence. Large values indicate structural defects are present. Selection probability tends to favor the most coherent options. We prioritize minimizing structural incoherence instead. We utilize 5 distinct structural sectors in our projects. The first sector is all about the concept of mathematical harmony. The second sector we are discussing here is known as balance. The third sector involves controlled activity and engagement. The fourth sector we need to discuss is connectivity today. Fifth point to consider is respect for structural constraints. Stability emerges from the complex interplay of various factors. We actively measure and analyze the critical coherence index. Complex structures often emerge in critical and pivotal regions. Dynamics describe possibility. Selection describes stability. Many questions still remain open today for further discussion. Join us on our exciting journey as we investigate further. Next, we will carefully examine the various field theories.
Welcome to the first part of this series on the structural selection principle. This series is not about esotericism or science fiction, but about a scientific question that arises directly from modern physics, complexity research, and field theory. Why do certain structures appear stable in nature, while other mathematically possible states are never observed? Modern physics normally describes the world through dynamics. That means we formulate equations of motion, field equations, or quantum mechanical states, and calculate the evolution of a system from them. But this is exactly where an interesting problem emerges. Many physical theories possess enormous numbers of mathematically allowed solutions. In nonlinear field theories, cosmology, or even quantum physics, there are often vast solution spaces. The equations allow many configurations. Yet in nature, we only observe a small subset of them as stably realized. The central question is therefore, why do some solutions persist, while others remain unstable or never become physically relevant? This is precisely where the structural selection principle begins. The basic idea is surprisingly simple. Not every dynamically allowed structure possesses the same structural quality. That means two states may both be mathematically correct, but one of them may be more coherent, stable, or robust than the other. The structural selection principle therefore describes an additional layer above pure dynamics. Dynamics still determines which solutions are possible. Structural selection then describes which of these solutions remain preferentially stable. One can imagine this as a landscape. Ordinary physical equations generate the entire landscape of possible states. The structural selection principle then describes which regions of this landscape become stable and physically relevant over long timescales. Mathematically, this introduces a structural cost function, f struct x. Here, x describes an arbitrary physical configuration. Small values of f struct mean high structural coherence. Large values indicate instability, inconsistency, or structural defects. This leads to a selection probability, p of x proportional to the exponential of negative f struct of x. This equation is important because it resembles statistical physics. States with a small structural cost function are preferred. States with high structural incoherence are suppressed. The decisive difference from classical physics is, here, the primary minimization target is not energy, but structural incoherence. This creates a new perspective on stability. To describe this structural quality more precisely, the model uses several structural sectors. The first sector is harmony. In this context, harmony does not mean something spiritual, but mathematical consistency. A harmonious system satisfies its equations of motion stably and without strong contradictions. The second sector is balance. Balance describes the relationship between activity and stability. Systems with extreme energy fluctuations or strong imbalances lose balance. The third sector is activity, or productive dynamics. A completely rigid universe might be stable, but it could not generate complex structures. Too much activity, on the other hand, leads to chaos. The model therefore favors controlled activity. The fourth sector is connectivity. This concerns correlations, synchronization, and coherence between different parts of a system. Modern physics increasingly shows that connectivity plays a fundamental role, from quantum correlations to cosmological structure formation. Additionally, a fifth sector is used, respect, or structural constraint fidelity. This refers to whether a system fulfills fundamental stability conditions. These include conservation laws, geometric consistency, or stability against perturbations. From these quantities emerges a definition of stability. Stability results from the interplay of all structural sectors. A system cannot truly be robust if one of the central areas fails. High activity without balance leads to chaos. High connectivity without stability can become unstable. High harmony without dynamics creates rigid structures without development. The structural selection principle therefore attempts to identify precisely those regions in which complex yet stable structures can emerge. A particularly important aspect is the so-called critical coherence index, or CCI. The CCI is a diagnostic parameter that measures how strongly the activity and coherence of a system are balanced. Very low values indicate excessive order, or rigid systems. Very high values point to chaotic activity. Between these extremes, a critical region emerges in which long-lived complex structures can appear. Exactly such critical states are interesting in many areas of nature: turbulence, phase transitions, galaxy formation, neural activity, complex field structures. The structural selection principle therefore does not attempt to replace the known laws of nature. Instead, it supplements them with an additional structural layer. Dynamics still describes what is possible. Structural selection describes what remains stable. Numerical simulations already show that certain structural configurations indeed appear preferentially. Particularly interesting is the fact that stable regions often emerge exactly where activity and coherence reach a critical balance. This suggests that stability in nature may not be accidental but instead arises from deeper structural selection mechanisms. Of course, this research is still in an early stage. Many questions remain open. How exactly should the structural sectors be defined? How can the model be connected to real observational data? Can testable predictions be derived from it? And how far does the principle actually extend? These are precisely the questions we will investigate step by step in the next parts of this series. In the next video, we will examine how structural selection can be formulated mathematically in field theories, and why classical energy minimization may not be sufficient to fully explain the observed stability of complex systems.
Welcome back to the second part of this series on the structural selection principle. In the first video, we explored the basic idea. The known laws of nature determine which states are mathematically possible. But the structural selection principle asks an additional question. Why do some of these states remain stable while others disappear or never become physically relevant? Today, we will take the next step and look at how this idea can be formulated mathematically. Modern physics describes many systems using so-called action functionals or actions. In classical mechanics, this is the action of a particle. In field theory, the action describes the dynamics of fields in space and time. From this action arise the well-known equations of motion. For example, the Maxwell equations of electrodynamics or the Einstein equations of gravitation. But this is exactly where a problem appears. Dynamics alone often generates enormous numbers of possible solutions. Especially in nonlinear systems, many mathematically allowed configurations exist. Stable solutions, unstable solutions, chaotic states, metastable structures, topological defects, oscillating fields. The equations themselves often do not uniquely determine which of these solutions will be physically preferred in the long term. The structural selection principle therefore extends dynamics with an additional structural layer. Mathematically, this is done by introducing a structural function, f struct x. Here, x describes an arbitrary configuration of a physical system. The core idea is, the smaller f struct is, the more structurally preferred the state becomes. At first glance, this resembles free energy in thermodynamics. But there is one crucial difference. The structural function measures not only energy, but structural quality. This includes, for example, coherence, stability, controlled activity, correlation, geometric consistency. The selection probability of a state is then described through an exponential weighting, px proportional to xemf. This means structurally coherent states have a higher probability of remaining stable over long timescales. The idea resembles statistical physics and maximum entropy methods. However, the goal here is not merely to minimize thermal energy. Instead, structural incoherence is suppressed. This naturally leads to the next question. How can structural quality be defined mathematically? For this purpose, several structural sectors are introduced. The first sector is harmony. Harmony measures mathematical consistency. In field theories, this can describe how well a configuration satisfies the equations of motion. Large residuals or strong instabilities reduce harmony. The second sector is balance. Balance describes the relationship between stability and dynamic stress. Systems with extreme energy fluctuations or strong imbalances lose balance. The third sector is activity. Complex structures require dynamics. A completely rigid system develops no new patterns. At the same time, activity must not become uncontrolled, otherwise chaotic behavior emerges. The model therefore favors moderate productive activity. The fourth sector is connectedness. Connectedness describes correlation and coherence between different parts of a system. Modern physics shows in many areas that such relationships are fundamental. Quantum entanglement, synchronization, collective dynamics, cosmic networks. The fifth sector is respect, or structural constraint fidelity. This concerns whether a system satisfies fundamental stability conditions. These include conservation laws, geometric consistency, stability against perturbations, physical admissibility. From these quantities emerges a structural definition of stability. What is important here is, no single sector is sufficient on its own. A system can be highly active, yet unstable. It can be strongly correlated, yet energetically unbalanced. Or it may appear mathematically consistent while possessing no complex dynamics whatsoever. The structural selection principle therefore favors systems in which these sectors interact coherently together. Another important step is the introduction of so-called defect functions. Instead of directly measuring perfect structure, one first describes structural defects: inconsistency, loss of coherence, instability, excessive activity, constraint violations. These defects are then transformed into normalized structural quantities. This creates mathematically stable values between 0 and 1. In this way, different physical systems can be compared with one another. This becomes especially interesting in numerical simulations. In nonlinear field theories, it can be observed that certain structure classes appear preferentially. Systems with balanced activity and high coherence persist significantly longer than chaotic or strongly inconsistent states. This is exactly where the connection to the so-called critical coherence index, or CCI, emerges. The CCI describes the relationship between activity and structural stabilization. Very low values correspond to rigid or over-ordered states. Very high values indicate chaotic dynamics. Between them exists a critical region in which complex, stable structures can emerge. This is particularly exciting because similar critical regions appear in many natural phenomena: turbulence, neural networks, biological systems, cosmic structure formation, nonlinear field dynamics. The structural selection principle, therefore, does not attempt to replace the known laws of nature. Instead, it describes an additional mathematical layer that explains why some solutions become structurally preferred. Dynamics tells us what is possible. Structural selection tells us what endures. In the next video, we will explore how concrete numerical simulations emerge from this framework and why critical coherence in nonlinear field systems may play a fundamental role in the stability of complex reality. Welcome back to the third part of this series on the structural selection principle. In the first two videos, we explored the basic idea and saw how structural selection can be described mathematically. Today, we move on to a crucial step: How do you actually test such ideas numerically? Because a theory only becomes truly interesting when it not only sounds philosophical, but also produces concrete simulations and verifiable patterns. That is exactly why the first numerical experiments with nonlinear field systems were carried out. Why nonlinear fields specifically? Because they possess an important property. They spontaneously generate complex structures. Unlike linear systems, nonlinear equations can. This makes them ideal test systems for structural selection. One particularly common model is the so-called phi-4 theory. This is a relatively simple field theory with a potential containing two stable minima. Although the model is mathematically comparatively simple, remarkably complex structures emerge from it. For example, so-called kinks or domain walls. These objects are locally stable transitions between different field states. They are topologically protected and possess a clear internal structure. This is where the interesting question begins. Why do some of these configurations remain stable while others decay chaotically? To investigate this, every simulated field configuration is analyzed using structural diagnostics. Among the quantities measured are: from these quantities, the critical coherence index, or CCI, is constructed. The CCI is not a new law of nature, but rather a diagnostic parameter. It measures the relationship between productive activity and structural stabilization. A simplified way to think about it is this. If a system is too ordered, almost nothing happens. If a system is too chaotic, every structure falls apart. In between, there exists a critical region where complex, stable patterns can emerge. This region is especially interesting. Numerical simulations show that long-lived structures frequently appear precisely where activity and coherence reach a critical balance. That does not mean that the CCI explains nature, but it could indicate that stability in complex systems does not arise randomly. Particularly fascinating is the observation that pure energy minimization is often insufficient to identify the configurations that are actually stable. A state with minimal energy is not automatically the most structurally relevant state. Some solutions possess slightly higher energy but remain significantly more stable because of their internal coherence. This is a central idea of the structural selection principle. Stability depends not only on energy, but additionally on structural organization. That is why simulations measure not only energies, but also informational and coherence-related quantities. For example, mutual information between neighboring regions of a field. These quantities describe how strongly different parts of the system are interconnected. Interestingly, it is often observed that systems with high local coherence exhibit significantly more stable dynamics. This leads to another important idea. Structure could play a role in physics that is similarly fundamental to energy. That does not mean energy becomes unimportant. Energy remains central to dynamics and interactions. But the selection of long-lived physical states could additionally be influenced by structural criteria. This is precisely where the connection between dynamics and selection emerges. the field equations still determine which states are mathematically possible. But the structural selection principle additionally describes which of these states are structurally favored to persist. This becomes especially exciting during chaotic transitions. Many simulations reveal a critical region between order and chaos. Too much order creates rigid systems without complex development. Too much chaos destroys long-term structures. Between them emerges a region of maximum complexity. This behavior resembles many other systems found in nature. Neural activity in the brain. Turbulence. Biological evolution. Self-organization. Cosmic networks. That does not automatically mean the same mechanism operates everywhere. But it suggests that critical coherence could be a general stability principle of complex systems. Another important point is the role of projection and observation. Later extensions of the model investigate whether some observed physical effects may not arise directly from additional matter, but instead from structural projection or coherence effects. This concerns, for example, cosmic expansion, structure growth, effective gravitation, apparent additional mass contributions. However, these ideas are still at an early theoretical stage and require significantly more numerical and observational testing. Therefore, it is important to emphasize the structural selection principle is currently not a confirmed physical theory. It is a research program. Its goal is to systematically investigate whether structural coherence actually plays a measurable role in the stability of physical systems. The simulations conducted so far provide initial indications that this could be possible. But many open questions remain. How universal is the CCI really? Which structural quantities are fundamental? How can the model be connected to real observational data? And which predictions truly distinguish structural selection from existing theories? These questions will define the next steps in this series. In the next video, we will explore how structural selection gives rise to a structural free energy, and why maximum entropy methods could play a surprisingly important role within this framework. In the previous videos, we saw that many physical systems possess an enormous number of mathematically possible states. The structural selection principle therefore investigates not only dynamics, but also the additional question: why do some structures remain stable while others decay? Today, we take a decisive step further. We will look at how this idea gives rise to a structural free energy, and why concepts from statistics, information theory, and maximum entropy methods suddenly play a central role. First, we must understand why free energies are so important in physics in the first place. In thermodynamics, free energy describes which states of a system are preferred. Systems often evolve towards states with lower free energy. However, in complex nonlinear systems, energy alone is often insufficient to fully explain stability. Why? Because two states can possess similar energy, while having completely different structural properties. One state can be. Another state, by contrast, can be. This is precisely why the structural selection principle introduces an additional structural cost functional, F struct X. This function measures not only energy, but structural quality. The fundamental selection rule is: states with lower structural cost are preferred. Mathematically, this leads to a probability distribution, Px, proportional to expect to F struct X. This equation strongly resembles statistical physics. And that is exactly what makes it interesting. Because suddenly a bridge emerges between field theory, information theory, thermodynamics, and statistical selection. Now, the decisive question arises. How does one define F struct concretely? One possibility is to introduce structural defects. Instead of directly measuring perfect order, one first describes deviations from structural coherence. For example, inconsistency of the field equations, loss of correlation, excessive activity, instability, violation of constraints. These defects are then transformed into normalized structural quantities. This creates stable quantities between 0 and 1. These quantities are often called supports or structural support fields. For each structural domain, one then obtains a contribution. Gamma A equals 1 over 1 plus dA. Here, dA represents the corresponding structural defect. When the defect becomes small, gamma A approaches the value 1. Large defects reduce the support. The crucial point is now, the structural free energy is constructed additively from these supports. One important form is FMAAT equals sigma lambda A log gamma. This equation possesses several interesting properties. First, it automatically favors states with high structural quality. Second, it strongly penalizes extreme defects while remaining numerically stable. Third, it directly resembles entropy and information measures from statistics. And this is exactly where the maximum entropy principle suddenly appears. The maximum entropy principle is one of the most important concepts in modern statistical physics. The basic idea is, if only limited information about a system is available, one should choose the probability distribution with maximum entropy, subject to the known constraints. Surprisingly, this very approach mathematically leads to exponential probability weights. And with that, a direct connection to structural selection emerges. The selection functional can therefore be interpreted as a relative entropy functional. This means nature may not simply select individual states, but statistically weight entire classes of structurally preferred configurations. This is a very important shift in perspective, because suddenly stability is no longer understood as an absolute state, but as a statistical property within a solution space. This becomes particularly interesting in complex nonlinear systems. There, many metastable states often exist. The structural selection principle proposes that those states preferentially persist, which possess. This gives rise to a kind of structural landscape. One can imagine this landscape similarly to energy landscapes in thermodynamics, except that structural properties are additionally taken into account here. Numerical experiments already show that certain classes of structures indeed appear preferentially. Particularly long-lived configurations are often located in regions of low structural cost. This does not mean that the theory has already been proven. But the initial results indicate that structural selection can be formulated in a mathematically consistent way. Another important point is the role of critical coherence. Between complete order and complete chaos, there often exist transition regions of maximal complexity. It is precisely there that long-lived patterns frequently emerge. The structural selection principle interprets these critical regions as zones of optimal structural balance. Too little activity produces rigid systems. Too much activity destroys coherence. Between them emerges a region of controlled complexity. Interestingly, similar transitions appear in many areas of nature. Turbulence, neural networks, biological evolution, self-organizing systems, cosmic structures. This does not automatically mean that the same equations apply everywhere. But it suggests that structural coherence may represent a general organizational principle of complex systems. That is precisely why the connection to information theory and maximum entropy methods is so important. Because it allows structural stability to be formulated mathematically as a statistical selection problem. In the next video, we will examine how these ideas can be applied to cosmology, and why structural projection effects might possibly play a role in expansion, structure formation, and effective
Modern cosmology follows the lambda CDM model. It describes an expanding, complex universe. Matter and energy define our reality. This model works remarkably well today. It explains the cosmic microwave background. It maps out large-scale structures. Galaxy distributions follow precise rules. The expansion history is mostly clear. Important questions still remain open. What is dark matter and its importance? What makes dark energy so uniquely specific? How do stable structures even arise? Why is the universe so incredibly balanced? Introducing structural selection principle. It investigates an additional possibility. Effects from structural selection possible. Einstein's equations define dynamics. A structural layer favors certain states. Ordinary gravitation remains fully intact. Structural fixes affect long-term stability. Creates an additional structural component. It depends on coherence and stability. Structural projection is an important idea. Dynamics are influenced by structure. Not all gravitation comes from matter. Space-time has emergent properties. Dark matter's existence
is not disproven. We investigate emergent structural effects. Local structural stability is crucial. Stability leads to only small corrections. Loss of balance raises effective gravity. This could explain galaxy-level gravitation. Initial simulations show promising results. Standard cosmology may be an approximation. Structural coherence is very important. A journey into the universe's structure.
Welcome back to the fifth part of this series on the structural selection principle. In the previous videos, we explored how structural selection can be formulated mathematically, and why statistical methods, free energies, and coherence play an important role. Today, we apply these ideas to one of the most difficult areas of modern physics: cosmology. Modern cosmology today is mainly based on the so-called alpha capital S DM model. This model describes an expanding universe containing visible matter, and dark energy. Remarkably, this model works very well in many areas. It explains the cosmic microwave background, large-scale structures, galaxy distributions, and large parts of the expansion history. Nevertheless, important questions remain open. For example, what exactly is dark matter? Why does dark energy possess precisely the observed strength? Why do stable cosmic structures arise in this particular form at all? And why does the universe appear to lie exactly at the boundary between order and complexity? The structural selection principle does not attempt to directly replace standard cosmology. Instead, it investigates an additional possibility. Could some observed effects partially emerge from structural selection? The central idea is the Einstein equations still determine the dynamics of space-time. But in addition, a structural selection layer could exist that favors certain cosmic states. Mathematically, this means ordinary gravitation remains intact, but structural corrections influence which solutions remain stable over the long term. In the simplest form, this produces an effective additional structural component. This additional component depends not only on energy, but on coherence, connectedness, stability, structural balance, and projection effects. An important concept here is structural projection. What does that mean? In complex systems, the observed dynamics can be influenced by internal structure. This means not every observed effective quantity must arise directly from additional matter. Part of the observed gravitation could theoretically result from structural properties of spacetime. This is a cautious but interesting idea. What is important here is the structural selection principle does not currently claim that dark matter has been disproven. It merely investigates the possibility that part of the observed phenomenology could emerge from emergent structural effects. For this purpose, an additional structural contribution is introduced. This depends on local structural stability. Put simply, if a region of the universe possesses high coherence and strong structural stability, only small additional corrections emerge. If, however, coherence decreases, structural balance is lost, or projection stress increases, then additional effective gravitational effects may appear. This creates interesting possibilities. For example, the observed additional gravitation in galaxies could partially arise from structural spacetime effects, without necessarily requiring new fundamental particles. However, this is still highly speculative and requires significantly more testing. Therefore, current research initially focuses on a more important question: Does the model remain consistent with observational data at all? This is precisely why the first cosmological simulations were carried out.
The following are investigated. HZ, meaning the expansion history.
Growth rates of cosmic structures.
Stability conditions. Effective density fractions.
And structural coherence parameters. The current results show something interesting. In certain regions, the model can remain very close to standard cosmology, while small structural corrections simultaneously appear.
This is important
because many alternative models fail to correctly reproduce known observations.
The structural selection principle,
therefore, deliberately does not attempt to generate large dramatic deviations. The idea is, rather, standard cosmology could be an effective approximation of a deeper structural selection process. Particularly interesting here is the role of so-called critical coherence.
The simulations once again reveal a transition region between excessive order
and chaotic dynamics. Exactly in this region, the most stable cosmic structures emerge.
This could mean that the universe does not randomly exist in a complexity-friendly state, but that certain structural regions are statistically preferred. Another important point is emergent robustness.
In newer extensions of the model, researchers investigate whether robustness itself emerges from the interaction of structural fields.
This means
stability would not be a fundamentally built-in property, but an emergent result arising from
harmony,
balance, activity, and connectedness.
This idea is particularly interesting because it aligns more closely with many known concepts in modern complexity research.
Indeed, in biological or neural systems, robustness often emerges not from isolated individual rules, but from collective organization.
Of course, many problems remain open.
For example, how can structural selection be connected with actual quantum field theory? How do precise predictions for cosmological observations emerge?
Can the model explain real gravitational lensing? And which differences from standard cosmology would even be measurable?
These questions are currently the subject of ongoing research. Therefore, the most important point is, at the moment, the structural selection principle is not a completed world model, but a theoretical research program.
Its goal is to systematically investigate whether structural coherence could play an additional fundamental role in physics. In the next video, we will explore how these ideas connect with quantum physics, information theory, and entanglement, and why coherence may play a deeper role in the structure of physical reality than previously assumed.
Welcome back to the sixth part of this series on the structural selection principle. In the previous videos, we explored how structural selection can be formulated in field theories and cosmology. Today, we turn to an area that belongs to the most fascinating and at the same time most difficult subjects of modern physics: quantum physics. Because it is precisely here that some of the deepest questions about reality, information, and coherence emerge. Quantum mechanics describes physical systems not through classical trajectories, but through wave functions and probabilities. Particles can exist in superposition states, describe multiple possibilities simultaneously, and remain correlated across large distances. Particularly well known is so-called quantum entanglement. Two particles can remain connected even when they are far apart. Measurements performed on one particle statistically influence the description of the other. Albert Einstein once described this behavior as spooky action at a distance. Today, we know that quantum entanglement is real and has been experimentally confirmed. Nevertheless, one fundamental question remains open. Why do stable quantum mechanical structures arise at all? Quantum mechanics allows enormous numbers of possible states. Yet, stable macroscopic reality appears only within very specific regions of this immense state space. This is exactly where structural selection becomes interesting. The structural selection principle proposes that not all quantum mechanically allowed states possess the same degree of structural stability. Some states could be more coherent, more robust, more strongly correlated, or more informationally stable than others. The central idea is therefore, quantum reality may not be determined solely by dynamics, but additionally by structural coherence. The concept of coherence becomes especially important here. In quantum mechanics, coherence describes the ability of a system to maintain stable phase relationships. When coherence is lost, decoherence emerges. Decoherence plays a central role in the transition between the quantum world and the classical world. A quantum system can contain many possibilities simultaneously. But through interactions with the environment, these possibilities lose their stable coherence. As a result, classical reality ultimately appears. The structural selection principle views this process from an additional perspective. The idea is, states with high structural coherence could statistically be more likely to persist. This does not mean that quantum mechanics is being replaced. The Schrödinger equation remains fully valid. However, structural selection could influence which coherent classes of states remain stable over long timescales. This becomes particularly interesting in entangled systems. Entanglement creates strong interconnectedness between different regions of a quantum system. This is exactly where a connection to the structural connectedness sector emerges. High connectedness means strong correlation, high mutual information, stable coherent structure. In modern quantum information theoretic approaches, information itself is already playing an increasingly important role. Some physicists already suspect today that space-time, gravity, or even geometry could partially emerge from deeper informational structures. The structural selection principle therefore operates within an interesting boundary region between field theory, information theory, complexity research, and quantum coherence. Another important point concerns critical states. In many quantum systems, particularly interesting properties arise near so-called critical transitions. There, systems exist between fluctuation and chaotic dynamics. These critical regions also play a central role in the structural selection principle. The Critical Coherence Index, or CCI, describes precisely this balance between activity and structural stabilization. Too little activity leads to rigid states. Too much activity destroys coherence. Between them emerges a region of maximal complex organization. Interestingly, many quantum systems display similar transition regions. For example, superconducting states, quantum phase transitions, Bose-Einstein condensates, or collective quantum dynamics. This does not mean that the structural selection principle already provides a theory of quantum gravity. And this is exactly where scientific caution is extremely important. At present, there is still no complete quantum field theoretic formulation of the model. There is no renormalized theory, no complete path integral quantization, no experimental confirmation, and no unified description of all interactions. What currently exists is a structural research framework. Its goal is to investigate whether coherence, connectedness, and structural stability may play a deeper role in physics than previously assumed. This becomes especially exciting when considering the question of space-time itself. Some modern approaches in theoretical physics are already investigating whether space-time could emerge from deeper networks of information. These include ideas from holographic physics, tensor networks, emergent gravity, or quantum information theory. The structural selection principle could theoretically be extended in similar directions. For example, one could ask, which spacetime structures possess maximal structural coherence? Which geometric configurations remain stable? And whether certain physical realities statistically emerge more frequently. However, these questions still remain largely open. The most important point is, therefore, the structural selection principle is currently not a replacement for quantum mechanics. It is an attempt to formulate additional structural principles that may help explain why stable complex reality emerges at all. In the next video, we will examine how these ideas could be applied to gravity and black holes, and why black holes in particular may represent one of the most interesting testing grounds for structural selection.
Welcome back to the 7th part of this series on the structural selection principle. Today, we turn to one of the most extreme and fascinating areas of modern physics, black holes. Hardly any object combines so many fundamental problems at once: gravitation, quantum physics, information, entropy, stability, and space-time geometry. That is precisely why black holes are a particularly interesting testing ground for structural selection. A black hole forms when matter is compressed so strongly that gravity dominates every other known force. According to classical general relativity, black holes are described in an astonishingly simple way. Essentially, only a few quantities are needed: mass, angular momentum, and electric charge. But this is exactly where the problem begins. Quantum mechanics says that information cannot simply disappear. Black holes, however, seem to trap information behind the event horizon. Then, Stephen Hawking discovered something even more surprising. Black holes radiate thermally. And suddenly, one of the greatest problems of modern physics emerges. What happens to the information? Is it lost? Does it remain preserved? Is it stored in the horizon? Or does space-time itself emerge from deeper informational structures? Because black holes are extreme systems in which stability, coherence, information, and space-time structure all play a role simultaneously. The structural selection principle therefore views black holes not merely as geometrical objects, but as structural configurations. The central question is, which black hole states are structurally stable enough to persist over long periods of time? The first domain is harmony. Here, harmony describes the consistency between gravitation and quantum information. The second domain is balance. Balance describes the relationship between mass, entropy, rotation, energy flow, and thermodynamic stability. The third domain is activity. Black holes are by no means completely static. They exhibit Hawking radiation, ring-down oscillations, accretion dynamics, jets, and quasi-normal modes. The fourth domain is connectedness. This is where things become especially interesting. In modern approaches to quantum gravity, entanglement may play a fundamental role for space-time itself. The fifth domain is respect, or structural constraint fidelity. This concerns stability of the horizon, consistency of space-time, avoidance of physical singularities, and robustness against perturbations. That means they are likely among the most robust structures known in the universe. Not every mathematically possible black hole geometry possesses the same structural quality. This creates a new perspective on the information problem. Instead of asking only, is information lost? One could additionally ask, which informational structures remain structurally stable? Another exciting point concerns entropy. Black holes possess enormous entropy, described by the Bekenstein-Hawking formula. But why this particular entropy structure emerges is still not fully understood today. This becomes especially interesting near critical transitions, for example, near unstable horizons, during Hawking evaporation, or in extremely rotating geometries. The structural selection principle, therefore, does not currently provide a finished solution to the information paradox. Stable physical reality may be determined not only by dynamics, but additionally by structural coherence. In the next video, we will explore how structural selection could possibly lead to a more general view of gravitation. This is an idea arising from deeper informational processes. Thank you for watching.
Welcome to the exciting first season finale of our show. We thoroughly explored the concept of coherence in field theories. Now, we take a bold step further in our journey ahead. What is gravity, and how does it truly impact our universe? Gravity is the result of the curvature of space-time around us. Matter tells space-time how to curve and shape the universe. Space-time is what tells matter how to move through it. This description works incredibly well and is very effective. It provides a clear explanation of planetary orbits and waves. And yet, despite progress, a deep problem still remains. One approach is geometric, the other is probabilistic. No single theory successfully unifies both of these domains. Physicists are on a quest to uncover a deeper description. A fascinating possibility emerges, capturing our imagination. It may be possible that gravity is not a fundamental force. Temperature arises from the movement and motion of particles. Gravity could emerge from informational structures. Space-time could potentially emerge from fundamental information, holographic principles, and quantum entanglement connections, preferring structures that exhibit maximum coherence overall. Not every geometry possesses the same level of stability. Black holes signify crucial boundary regions in space. Matter changes the structural integrity of substances. Stability is defined as a state where harmony and balance exist. A radical shift in our perspective is necessary for growth. Scientific caution remains extremely important in all research. Great theories always begin with a specific perspective. What are the reasons behind the persistence of certain structures? Coherence and information are truly fundamental in communication. The solution to the problem is found in the structure itself.